This lesson is going to show you how to calculate the KEQ value from initial concentrations and coming up with the equilibrium concentrations in order to place them into the expression. When you are asked to solve for a KEQ value and the concentrations are not at equilibrium, we have to use something called an ICE chart. And ICE is an acronym for initial concentration, change in concentration, and then the equilibrium concentration. So in the previous lesson, you actually did an example of where you calculated a KEQ value, but all the concentrations were already at equilibrium. If you notice that some of them are initial concentrations, then what we have to do is a little bit of work in order to obtain the equilibrium concentration. So we set up something called an ICE chart, where we start off with initial concentrations. We take a look at the change in concentration that's going to happen. And this is where we would use some stoichiometry and look at mole ratios in order to do that. And then we're going to calculate the equilibrium concentration by taking whatever the initial concentration is and then adding or subtracting, because it does depend whether it's reactant or product. So we should say plus or minus here, the change in concentration. And then once you know your equilibrium values, then you can plug it into your KEQ. And just a reminder that everything always has to be in molarity or molar concentration. So here is an example where we want to solve for KEQ, but not all of the concentrations are at equilibrium. And you can tell, because it says when 0.25 moles of SO2 and 0.2 moles of oxygen are placed in a 10-liter vessel. This is the initial values, right? We can tell they've taken these amounts, they've put them into a 10-liter container. Then they probably close the lid, let it go, and then the reactants make products. The products will start to make reactants back and forth until the rates are equal. Then it says the equilibrium mixture was found to have 0.162 moles of SO3. That's the only equilibrium concentration that I know currently. So we have to calculate the KEQ. One thing you should notice is that I don't have molar concentrations for anything. So what we want to do is we want to calculate the molar concentrations of our substances. So let's calculate the molar concentrations of all of these substances. So we see that we have a mole value here. So I'm just going to do concentration, molar concentration of SO2 initially is going to be my mole value divided by my volume in liters. So these are pretty easy calculations because the volume is is 10 liters. So we're just dividing everything by a factor of 10, which just moves our decimal place over 1. So we're going to get 0.0250 molar. And so for all of the rest of these calculations, we're just going to move that decimal over. Of course, if you had different liters, you would spend some time coming up with the concentration of everything first. We're going to move over here to our actual equation, and we're going to set up an ICE chart. So an ICE chart is the initial, the change, okay, for C, but I always use a delta symbol, and then E, and I always write EQ, okay, for equilibrium. And then we just go along and we fill in everything that we know. So we know that the concentration of SO2, we just calculated it, is 0.0250 molar. Now I could put capital M in here, and I will for now, but it's not necessary because it's assumed that all of these are molar concentration. Here's my initial amount of oxygen. Again, I got to divide that by 10 liters. So I'm just going to move that decimal over, 0.0200 molar. Initially, I have no product. So initially, my SO3 amount is 0. I know that they gave us a value over here, but remember, this was at equilibrium. So that's not the initial. And then we're going to move along and we're going to look at the change in concentration over time. So notice that I have coefficients of 2, 1, and 2 in this particular equation. When SO2 and oxygen start to react and collide, you need twice the amount of SO2 compared to oxygen. And these concentrations are going to go down, right? Because we're going to make products. So what will happen is the concentration of SO2 is actually going to decrease by some amount. So some amount of 2x because of that coefficient. And the concentration of oxygen is just going to decrease by x. So they're going to decrease by the same amount. SO2 just twice the amount because of the coefficient. SO3 is going to increase over time, right? Because reactants are going to collide and make products. And it's going to increase by twice the amount because of that too. So remember, at equilibrium, we take the initial concentration plus the change. So at equilibrium, we're going to have 0.0250 minus 2x for SO2. We're going to have 0.0200 minus x for oxygen. And then at equilibrium, we know the concentration of SO3. And remember, we got to divide by 10. So it's going to be 0.0162 molar. So it's very important that you set up the ice chart properly. Once you do, all the rest of it is just math skills. But make sure you're aware of the coefficients. Make sure you're aware that reactants decrease over time in concentration. Products increase over time. Make sure you're aware what these values are telling you. Are they telling you initial amounts? Are they telling you equilibrium amounts? And then from here, what we need to do is solve for these x terms right here. And then we'll have all of our values at equilibrium and we can plug them into the KEQ expression. So the first thing that we need to do is we have to solve for x. And we can solve for x because of this right here. So we know that initially we had no SO3. The change was 2x. So we know that 2x is equal to this equilibrium concentration of 0.0162 molar. So this is a good thing. And all we have to do is take that 0.0162 molar and divide by 2. And then my x term is equal to 0.0081 molar. So what we could do here is I would, be tempted to solve for the equilibrium concentrations of both my reactants. So let's do now concentration of SO2 at equilibrium. So notice how I put these little subscripts of I or EQ, just so we keep everything straight. And so I should have 0.0250 minus 2x. Okay, so 2x is equal to 0.0162 molar. And when I subtract that off, I get a value of 0.0088 molar. And I can have 4 decimal places. Okay, so this is good. We can hang on to that. I'll just move over here. I want to do the same thing. I want to solve for the concentration of oxygen at EQ. And that is 0.0200 only minus x alone. So I'm going to take 0.0200, subtract off my x term, which is 0.0081. And when I do that, I get a value of 0.0119 molar. So now I have all of my EQ concentrations, right? They gave me the value over here of the product. I now know both of my reactants. So now what we can do, step 3, is we can solve for the KEQ value. And again, we're going to take concentration of SO3 squared. Do not forget that those coefficients become their powers. And we're going to divide by my reactants, concentration of SO2 squared times the concentration of oxygen, not squared, just to the power of 1. So let's sub in our values, 0.0162 squared. And again, everything's coming out of this line right here, okay? SO2, we have to solve for that. So it's 0.0088 squared times oxygen, 0.0119 to the power of 1. When you sub all your numbers in and then divide your reactants and your products, you should end up with a KEQ value of 284.79, but we still have to be mindful of significant figures. And in our expression here, I have 2 sig figs for the concentration of SO2. So I need to put this as 2.8 times 10 to the 2.